In the do now question, it says, Al says, if ABCD is a parallelogram, then ABCD is a rectangle. And it says, sketch a quadrilateral ABCD that shows that Al's statement is not always true. So if I have a parallelogram, it doesn't necessarily have to be a rectangle. It could also be a rhombus. So, for example, if I sketch parallelogram ABCD that not only has opposite sides congruent, but in fact, if all the sides are equal, then it would not only be just a parallelogram, but it would be a rhombus. But it wouldn't be a rectangle because rectangles don't have four equal sides. They're not equilateral. Rhombuses are, but rectangles are not. So this would be an example of a parallelogram that's not also a rectangle. Or instead, we can just have quadrilateral ABCD that's just a regular parallelogram. So for example, if these angles are 120 and these angles are 60 degrees, this is a parallelogram because opposite angles are congruent to each other, but it's not a rectangle because in a rectangle, all four of the angles would be right angles. For question number 2, it says we have a rhombus, and it says that the diagonals intersect at point T, that PR is 16, and that QS is 30. Now remember, rhombuses also have all the properties of parallelograms. So the diagonals bisect each other. So I know that this diagonal is split equally, and this diagonal is split equally as well. So I'm just going to write 8 and 8, 15 and 15, since the 16 is being split in half, and the 30 is being split in half as well. So let me just clean this up a little bit so it's not as confusing. So this one's being split in half, and that would be 8 and 8 to total 16. And this diagonal is also being split in half, and that would be 15 and 15 to total 30. We also know that when we have a rhombus, the diagonals are perpendicular to each other, so they form right angles. What we have here are 4 different right triangles. They're all the same, so I'm just going to focus on one of them in particular. This right triangle, we already have both of the legs. This leg is 8 and this leg is 15. So what we actually need to do is we need to find the hypotenuse. This is the hypotenuse because it's opposite from the right angle. So I'm going to put a question mark over here because what we need is the hypotenuse of that right triangle. So when I have two sides of a right triangle and I want to find the missing one, I think Pythagorean theorem, and I have the legs 8 and 15. So I'm going to plug in those legs for A and B, and I'm trying to find the hypotenuse, which is C. So that's 54 plus 225 is equal to C squared. And that is 289 for C squared. To get C by itself, we're going to take the square root of both sides. So C is equal to 17. So the side of the right triangle that we just found the hypotenuse is 17. And we know that this quadrilateral is a rhombus, and rhombuses are equilateral. So if this side is 17, all the sides of this rhombus are 17. So all I have to do is add up 17, 17, 17, and 17, 17 4 times, and I get the perimeter of the quadrilateral, which is 68 units. As we spoke about briefly yesterday in class, a quadrilateral is a square if and only if it is both a rhombus and a rectangle. So in order to prove that we have a square, the very first thing we need to prove is that we have a parallelogram. And then beyond that, we need to prove that it has a rhombus property and a rectangle property. And then we'll know for sure that we have a square. Once again, you don't need to prove every property of every single quadrilateral. One from each is enough: a parallelogram property, a rhombus property, and a rectangle property. The order of these two don't matter, but parallelogram does need to come first because before something can be a rhombus or a rectangle, it first needs to be a parallelogram. Notice on our parallelogram family tree, everything connects to squares because squares are everything. Parallelograms, rectangles, and rhombuses. They have all the properties of all the other ones because they are everything. Take a look over here. It says that we have square, L, M, and O, with diagonals that intersect at P. And what we need to do is prove that OP is a median and an altitude of triangle NOL. I'm going to highlight triangle NOL for a second. So here's the triangle we're focusing on, and we're trying to show that OP is both a median and an altitude of this triangle. So a median connects midpoint to opposite vertex. So we basically first need to show that P is the midpoint of the side of the triangle. Because if we can show P is the midpoint of the side of the triangle, we'll know that this is the midpoint connected to the opposite vertex, so we'll know that this is a median of the triangle. So I'm going to think about, since Ln is a diagonal, I'm going to think about diagonal properties that I know about, and everything applies. Parallelograms, rectangles, rhombuses, because we do have a square. So since my goal is to say this, well, that's due to the fact that diagonals bisect each other, right? Because a parallelogram property that also applies to rhombuses is that the diagonals bisect each other. And since the diagonals are also congruent because a square is a rectangle as well, in fact, all the pieces are congruent to each other as well because not only are they being split in half bisected, but the whole diagonals are the same as each other as well. Don't need that for this question though, so I'll get rid of it to make the diagram less confusing. So because diagonals of a parallelogram and also a square bisect each other, we know that LP is congruent to PN. So we know that P is the midpoint of LN because it's splitting this into two equal parts. And then we know that OP is the median of the triangle because we know it's connecting midpoint to opposite vertex. I'm going to pause the video and write this up in the proof. You should try on your own paper as well, just up to proving that OP is a median, and then you can check your work with the video, so definitely press pause here. Feel free to pause the video here to take a look at the written up proof, because I am going to move on to the next part of the proof statement now. Now we also have to prove that OP is an altitude of triangle NOL. So an altitude is just a perpendicular line to a side of the triangle that passes through the opposite vertex. So in order to show that OP is also an altitude, I just need to show that there's right angles over here. So I'm going to just draw those in so you can see what my goal is. So I want to say that there's right angles here. And I actually know that because I have a rhombus, because a square is a rhombus. And one of our properties of a rhombus is that the diagonals intersect to form 90-degree angles. They're perpendicular. So in fact, because diagonals of a rhombus and also a square have perpendicular diagonals, these are all right angles here, but I only need these ones for the question. So I'm going to get rid of it to make it less confusing. So I'm going to put this into the proof. And it's going to be one more step to say that these are right angles. And then another step to say that this is the altitude. So pause the video, try to write it up yourself. I'm also going to pause the video and write it up also. Okay, so that was just two more steps of my proof. All I needed to say was that these were perpendicular to each other, and that's because diagonals of a rhombus are perpendicular. I'm actually going to change that because we do know that we have a square here, so I don't want to get confusing. So I'm just going to write that that's because that even though that's a rhombus property, that diagonals of a square are perpendicular because all of the properties of rhombuses apply to squares, and we are talking about a square here. And then, since an altitude is just a perpendicular line, then I can say OP is the altitude of triangle LON because an altitude is a perpendicular line to a side of a triangle that passes through the opposite vertex. And that's what we have here. We have a line that's perpendicular to a side of the triangle that also passes through the opposite vertex, vertex O here. Okay, moving along. Next example, we are given that CDAB is a parallelogram, so just a parallelogram, nothing else. We know that BDC is, so that angle is 4x minus 2, so I just put an arrow to indicate the angle that it's talking about. DBA, that angle is 3x plus 6. An angle DBC this angle right here is 2x plus 14. It says to show that CDAB is a rhombus but is not a square. So to be a rhombus, we know it's a parallelogram, so we just need to show a rhombus property. And then if it's not a square, then it's not going to be a rectangle, because remember, squares both a rhombus and a rectangle. So then we have to show that it's not a rectangle. I know it's a parallelogram, so I know that opposite sides are parallel. And that's super important here because you might have noticed that there is a letter Z, and two of the angles, the ones in green that we were given information about, are alternate interior angles. And we know alternate interior angles are congruent when we have parallel lines cut by a transversal. And it's a show here, it doesn't say prove. So I'm not going to prove it. I'm not going to write the two-column proof, it's a show. So I'm going to set the two alternate interior angles equal to each other. I'm going to subtract 3x from both sides. And I'm going to add 2 to both sides. Divide by 4. And now I'm going to just take that x value and I'm going to plug in to find the angle measurements. So 3 times 2 is 6, plus 6 is 12 degrees. Over here, 2 times 2 is 4, plus 14 is 14 plus 4 is 18. Oops, I made a mistake. Let's backtrack. I made a mistake in my solving. Okay, let's go back. And sometimes that happens. It's the smallest things. So that is x minus 2 is equal to 6. So x is equal to 8. My bad. Sorry about that. So 8 times 3 is 24. That's 30. That's why I was wondering why those numbers were not working out correctly. 8 times 2 is 16. Plus 14 is also 30 degrees. So I'm going to stop right there. It's a rhombus, as we can see, because the diagonal is bisecting the angle. This angle here is being equally split in half into 230 degrees. So CDAB is a rhombus because diagonals bisect angles. And it's not a rectangle because the angle is not 90 degrees. And rectangles have all 90-degree angles. The next part says find the measure of angle AMB. So if this is a rhombus, the diagonals are perpendicular, so where they intersect, there's right angles. So AMB would be a 90-degree right angle. And BAD, well, it's not a right angle because this is not a rectangle. So we do know that rhombuses have parallelogram properties, and we know it's a parallelogram. So remember, consecutive angles are supplementary. So if the whole angle B is 60 degrees, this whole angle A needs to be 120 degrees because that's what makes 180 with 60 degrees. And the diagonals, oh wait, we don't need to even bisect it because it was just asking for the whole angle BAD. So the whole angle BAD is 120 degrees. That's angle A. Remember, consecutive angles of a parallelogram are supplementary. Okay, moving along over here, we know that JKLM is a parallelogram. So we know a lot of stuff about JKLM. And JM is congruent to LN. And once again, I recommend you pause the video and actually try to do this first on your own. We also know that angle LMN is congruent to angle LNM. And we need to prove that JKLM is a rhombus. First, I'm going to try to draw any conclusions that I can, and I'm going to try to plan my proof. And this one's actually really simple, because over here, I have two congruent angles in triangle LMN. So triangle LMN is also going to have two equal sides. And those sides are going to be located across from the congruent angles. So side LN and side LM, once again across from the congruent angles, are going to be congruent to each other. And since these are congruent and these are congruent, well, these need to be congruent to each other because both of these are congruent to the same LM. So JM and LM need to be congruent to each other. And since we already knew JKLM is a parallelogram, we don't have to prove it's a parallelogram, we already know it. So now we know it's the rhombus because it's got two congruent consecutive sides. And that's it. This is going to be a really, really, really short proof. So I'm going to pause and write it up. Try to write it up yourself as well. Definitely pause the video and try. Okay, so here I have my proof completely written up. So notice over here, I have that LM is congruent to LN. That was because we had congruent angles in the triangle, so the sides opposite are congruent. That's not base angle theorem, by the way. That's converse of the base angle theorem. We're starting with the angles and we're concluding about the sides, so that's why it's just better if you just write it out in words like I did. Then I have that JM is congruent to LM, and that's my transitive property. And that's because from our givens, we had that JM is congruent to LN. And then from the converse of the base angle theorem, we just proved that LM was congruent to LN. So both LM and JM are congruent to the same segment LN. Since they're both congruent to LN, they need to also be congruent to each other. Oh, I just wrote this incorrectly. That should be an M. JM is congruent to LM. That's what we need, the two sides of the quadrilateral. Once again, since JM and LM were both congruent to LN, they needed to be congruent to each other. We can see it here too. They were both congruent to LN, so they have to then be congruent to each other. So then we know it's a rhombus because a parallelogram with two congruent consecutive sides is a rhombus. Moving on to the next proof. So here we just have a quadrilateral. We don't even know if it's a parallelogram or not. It's literally just a quadrilateral. I don't know anything about it. And we know that AE, so here's AE, is congruent to FC. We know that BF is perpendicular to AC, which means it forms a right angle where it intersects it. And we know that DE is perpendicular to AC, so we know it forms a right angle where they intersect. And we know that angle 1 is congruent to angle 2. And our goal here is to prove that we have a parallelogram. Well, I already, in these two triangles, ABF and CDE, I already have angle 1 and angle 2. That's a pair of congruent angles. And I also already have the two right angles. So that's another pair of congruent angles. And I have information about side AE and side FC. But those are longer than the sides of the triangle that I'm actually interested in, that I have information about. But if I make them smaller, if I subtract, then I can get AF and DC, and that will give me angle side in the two triangles. And after I have two congruent triangles, I can definitely use CP/CTC to get more information that would help me prove that I have a parallelogram. So that's kind of my goal at first. So let's pause the video. Let's write up the proving the triangles congruent. Make sure they include your subtraction. I'm going to do the same thing. And then you can resume the video when you are done. You can check your work, and then you can move on to actually using CP/CTC to prove that you have a parallelogram. So here's my proof so far, just to prove the triangle's congruent. So I didn't write the given, sorry, I don't have a lot of space here. So our first congruent pair of angles for AAS comes from the givens, from angle 1 congruent to angle 2. And then our second congruent pair of angles comes from the conclusion from perpendicular lines. From knowing that we have perpendicular lines, I know that they're right angles, and all right angles are congruent. So I just combine that into one step. Both of the angles are congruent right angles. And I put my reason, my combination, perpendicular lines form right angles, and all right angles are congruent. Then for my subtraction, I first need to state that FE is congruent to itself by reflexive, because I'm going to be subtracting it from AE to get AF, and I'm also going to be subtracting it from FC to get EC. So here I have my actual subtraction. AE, take away EF, leaves us over with just AF, and FC, take away FE, just leaves us over with EC, which is what we need. So my subtraction step, where I'm actually subtracting, is subtraction. And then this minus this is that, this minus this is that, so that's substitution. And then I have what I need to prove the triangle's congruent by angle side. So now I have to think about how I can use CPCTC to get more information to prove that I have a parallelogram. And I'm going to CPCTC this side and this side, A, B, and CD. I'm going to put that into my proof. So AB is congruent to CD, and that's going to be by CPCTC. And I'm also going to CPCTC something else. And what I'm going to CPCTC, oops, let me scroll down a bit so I have more space. I'm going to also CPCTC this angle here. That's an angle in triangle ABF. And this angle here, the two in red, that's an angle in triangle CDE. And I'll explain why in a second. So let me put that here. Angle BAF is congruent to angle, what is that, DCE, that red angle. Yes, you do need 3 letter names for these angles, else I don't know which angle you're referring to. And the reason that I CPCTC'd those angles is because those angles are alternate interior angles. So now that we know that those alternate interior angles are congruent, we can say that the sides forming those alternate interior angles, which are AB and DC, are parallel to each other. So I'm going to put that over here. AB is parallel to DC. And my reason for that is if alternate interior angles are congruent, then lines cut by a transversal are parallel. And now I have enough information to prove that I have a parallelogram. I'm just going to continue up here. I'm going to label it step 9. Now I know that ABCD is a parallelogram, and that was my goal. And the way I showed that is I showed that one pair of opposite sides, AB and CD, was both congruent and parallel. If one pair of opposite sides are both congruent and parallel, the quadrilateral is a parallelogram. Oops, moving along to the exit ticket. Let me scroll down over here. I needed more space for that last one. What properties of squares would you use to find the values of x, y, and z below? Okay, so I know it's a square. So in a square, all sides are equal to each other. So I'm going to take x squared, and I'm going to set it equal to 2x squared minus 4 because they're both sides of the square and they have the same variable. This is a quadratic. Let me try the move step over. So I'm going to move the x squared over. Oh, actually, let me not do that. Let me move the 2x squared over. That might be a little bit easier. So I'm going to subtract 2x squared from both sides. That cancels out. And that would be negative. X squared equals to negative 4. Divide by negative 1. X squared equals to 4. So we have x is equal to 2 if we square root both sides. So I found the value of x. 2 squared is 4. So now I found the value of y because all the sides are equal. Z is on the angle, and we know squares have all the properties of rectangles, so they have 90-degree angles. And we know that they have all the properties of rhombuses as well, so we know that the diagonals bisect the angles. So that would be half of 90, which is 45 degrees. And there we have it.